Hello students, welcome to EPG Pathshala. I am Dr. Nasir Iqbal from the Department of Physics, University of Kashmir, Srinagar. Today we are going to talk on classification of variable stars under the paper Astronomy and Astrophysics. After completing this module, the students will be able to learn a few basic rules for classification of variable stars, to know that how to recognize a particular group of variable stars having very high luminosity, to learn the concept involved in the classification of type 1st and type 2nd Cepheid variable stars. To know that the observation of classical Cepheid variable stars are the best large scale distance indicators, and the binary stars and variable stars are altogether different as per star classification, and the basic criteria for classification is the variation in the output radiation from variable stars. Observations reveal that the luminosity changes that take place in a variable star are due to the changes in its internal physical mechanism. Such stars are therefore known as intrinsic variables. There are stars whose luminosity variations are only apparent and are caused by the obscuration of their light by some companion stars or the dust. These types of variable stars may be called the extrinsic variable stars. In this lecture, we will focus our attention almost entirely on the intrinsic variable stars. In order to understand the detailed characteristics of the stars observed most frequently in our own galaxy, as well as other extragalactic structures, it is important to classify the stars of variable brightness into different categories based on some known parameters like luminosity, magnitude, the apparent magnitude and the absolute magnitude, and distance from Earth. Two groups of type 1st and type 2nd variable stars have been identified so far. Type 1st group is known as classical Cepheid variable stars, and type 2nd group is simply called the Cepheids. The Cepheids, irrespective of their type, are the best indicators for determining their distances from the Earth. So, let's describe the classification of variable stars. While talking about the classification of variable stars, we will first talk about the extrinsic variable stars. The apparent luminosity of all the extrinsic variable stars keep on changing periodically due to eclipsing of their brightness by some other star or a cosmic object. Binary and some groups of multiple stars constitute these types of variable stars. The real binary systems are physical pairs which describe orbits around their common center of gravity under the influence of their mutual gravitational attraction. Based on their closeness and mutual orientations, the binary stars are further subdivided into three types, namely the visual binaries. They eclipsing binaries and the spectroscopic binaries. Visual binary is a pair of stars whose binary nature can actually be detected through a telescope. This is possible either when the distance of the pair from the Earth is not large or when their mutual separation is appreciably large. For the identification of the individual members of the binary, the angular separation must be greater than 0 degree 50. The period of revolution of visual binaries ranges from about a year. More than 65,000 visual binaries have been so far discovered. There are many binary systems whose orbital planes deviate from the perpendicular line of sight. This deviation in the line of sight makes it possible for the individual members to eclipse each other during the course of their orbital motion. When individual stars in a given binary are very close together so that their resolution into separate components is impossible, their binary nature is revealed using Doppler shift technique. Such a binary system is known as spectroscopic binary simply because there is only spectroscopic method available to identify them. More than 1000 spectroscopic binaries have been identified so far by using the Doppler phase shift technique. In the given figure, we have a timeline orbital motion of a binary star configuration. Along the horizontal axis, we have the time, and along the vertical axis, we have the intensity. So we have 5 phases of these binaries shown here. In the second and the third and the fourth type of binaries, the other star is well defined. Both of them are supposed to orbit around a common center of mass. While as in the first one and in the last one, the second star is not visible. But if we see their visibility, it can be found out their visibility is same as what we have seen in the first three, but it is only as per different time periods, depends upon the line of sight. Sometimes they are seen and sometimes they are not. Intrinsic variable stars. The apparent brightness of intrinsic variable stars undergoes a perceptible change only when some physical changes occur in an individually observed star. In other words, the intrinsic variable stars do not necessarily form a binary system. An individual star undergoes a physical change through a variety of natural phenomena, say for instance, nuclear reactions taking place in the outermost layers qualifies it to be an intrinsic variable star. We can subdivide the intrinsic variable stars into two major types, namely the pulsating variables and the exploding variables. As far as pulsating variables are concerned, the change in their luminosity are mostly regular and periodic. These variable stars can be distinguished on the basis of the length of their periods, nature of variation of the light output, and their spectral characteristics. These are unstable, old age stars almost near the completion of their life cycle. The Cepheid group of variable stars forms one of the major subclass of the intrinsic variable stars. In this very module, we try to explain the nature of some of the important Cepheid variable stars through spectrum analysis. There is yet another intrinsic group of stars which belongs to the intrinsic variable category. These individual stars are called eruptive or exploding variables and are identified by a sudden or violent flaring up of radiation. These include novae and supernova stars. Nova stars undergo occasional outbursts, whereas supernova stars are characterized by the violent and continuous outbursts of energy in the form of electromagnetic radiation and mass ejections. So, we should know some classification of these variable stars. We have here a list of some well-known variable stars. The list is not exhaustive but has been included to appreciate the discovery of variable stars through the course of human history. So in the given table, we have the following rows: 1, 2, 3, 4, 5, 6 and 7 rows. In the first row, we name the constellation. The second row, we name the discovery, the name of the person who have discovered it, and exactly also the date when it has been discovered. In the third row, we have the apparent magnitude, and in the fourth row, we have the other magnitude, which is a mini number. In the apparent magnitude, we have the maximum. Here we have the mini number magnitude, and then we have in the other row, we have the range of magnitude, and then we have the period of its oscillation and also the type of this binary. The first one is Andromeda. Let me check few of them. The first one is Andromeda. It has been discovered by Ernst Hartwig on August 20th in year 1885. Its apparent magnitude is 5.8 and the mini magnitude is 16. The range of magnitude varies is somewhere in between the 10.2, and its period of oscillation is not shown here, but its type, that which type it belongs to, that is the supernova first. When we talk about the supernovae are usually the final stage of this star evolution. It's important to mention here that in a star evolution we have three stages. The first one is the protostar evolution, means the pre-main evolution. Then the second one is the main sequence evolution, so we call it simply the main stage evolution. And the last one is the late stage evolution, and in the late stage evolution we have even the supernova. But supernovae are of different types. So we have the type 1 and the type 2. So this one, Andromeda, belongs to the type 1 supernova. So the other variable stars belong to different constellations. So are like this: Aquila, Acaris, Auriga, then we have the Capricornus, then we have the Carina, then we have the Cepheid, we have one more Cepheid, we have one more Cepheid, then we have Cetus, then we have a Cancer, one more Cancer, we have Corona, Borealis, we have Cygnus, we have Gemini, we have one more Gemini, we have one more Gemini, and we have Hercules, we have Hydra, and then we have one more Hydra, we have Leo, we have Lyra, we have Orion, we have one more Orion, we have one more Orion, we have Pegasus, we have Pegasus, we have one more Pegasus, we have Pisces, we have Sanctum, we have Serpens. So we have Serpens one more, and we have Taurus, we have Taurus, we have Virgo. Now these are the names of some of the binaries lying in these given constellations. So we have also shown here exactly the date of their discovery with their different kind of magnitudes and also to which class they belong. So this classification just makes us feel that variable stars are exactly varying in the brightness and the magnitude. It's not only that we can have only one kind of variable stars, but we have different types of variable stars illustrated in this very table. Now we have one important type, we call them Cepheid group of variable stars. And this Cepheid group of variable stars, they have also two types. So we call it the type first Cepheids and the type second Cepheids. This type first Cepheid, we talk about this classical Cepheids. So Delta Cepheid is regarded as one of the earliest recognized members of the group of about 600 stars in the Milky Way galaxy with an absolute magnitude ranging from -1.5 to -6. As we talked about the Milky Way galaxy, we all know that Milky Way galaxy is the galaxy in which we live. So this Milky Way galaxy, if you see that, where is our Milky Way galaxy and how far it is from our solar system? Just for an information here, our solar system lies at a distance of 10 to 15 kiloparsec from the center of our Milky Way galaxy. Now coming back to this type, we have said that this Delta Cepheid is the earliest recognized members of the group of 600 stars. This indicates that the brightest of these variable stars are about 10 to the power 4 times more luminous than the Sun. Some of the brightest known stars among these are the Polaris, Delta Cephei, Eta Oculi, Zeta Geminorum, and Beta Doradus. The period of variation of light for these classical Cepheids range generally from 2 to 45 days, although most significant and usual range is 5 to 10 days. Almost all the classical type first Cepheid variable stars are yellow supergiants with spectra varying between F and K. The direct observation of these stars suggests that they are strongly concentrated near the equatorial plane of the galaxy and are believed to belong to the extreme population first stars. It is a well-known fact that when we talk about the classification of the stars, we also classify them on the basis of their own population. Means that how much they exist in the given area. So we have the population first stars and we have the population second stars. Here we refer the type first Cepheids belonging to the population first stars. Now we have a light curve here. So in this very light curve, this curve represents the variation of light with period, and the lower one indicates the variation of radial velocity with period. Before we proceed, so what is a light curve? Light curve is actually how much light coming from the star, means that the number of photons counted per second received by the detector of any telescope is plotted against the time period. That shows that how this object varies in brightness. So that is actually the light curve. If one plots the change in the apparent magnitude of a variable star against the time of a measurement through a complete period. One obtains the curve that is called the light curve of the variable. In one complete period, this light curve changes through one complete cycle, that is, from crest to crest or from trough to trough. Different types of light curves are exhibited by type first classical Cepheids, depending mainly on the length of their periods. Delta Cepheid and its close companion star, with a period between 2 to 6 days, brighten more rapidly than they fade and have very smooth light curves. Eta Equali and other stars with a period in the range from 7 to 8 days have pronounced hump on the descending branch of the curve. The curve becomes very symmetrical, rising and falling at almost equal rates. So following set of figures show some of the Cepheids having variation of apparent magnitude with periods in days, as we have already explained. Now we have these different kind of light curves showing with different features. All these curves depicted here have been obtained from a very fundamental book on astrophysics that was published by Prince's Hall of India Private Limited. Now finally, the rise to maximum is again much more rapid than decline to minimum in case of the stars with periods much longer than 10 days. This can be easily understood by critically analyzing the spectrum of the Cepheids. This spectrum includes observation of radial velocity variations, which indicate the nature of pulsation mechanism of these stars. The radial velocity variation is found to be strongly correlated with the variation of light curve. The variation in velocity ranges from -20 through 0 to +20 km per second. In any spectra for the type first Cepheid stars, the variation of light and radial velocities are plotted with reference to the period of delta Cepheid. Conventionally, the velocity of approach is considered a negative radial velocity, whereas positive velocities are attributed to the receding variables. The velocity curve is very much like the light curve reflected on a horizontal plane. The maximum for the light curve occurs at a point where the velocity curve reaches the minimum and vice versa. For Cepheids having significantly longer periods, the light curve attains the maximum distinctly before velocity curve reaches its minimum. Some of the important conclusions drawn from the spectra of the Cepheid variables are: number 1, the Cepheids exhibit nearly normal FGK class spectra at minimum light. Number 2, the spectra type at maximum light usually ranges from F5 to F8. Number 3, the spectra at maximum light are not normal. So, classical Cepheids are primarily recognized by the presence of G band. Iron first, iron second lines means Fe first and Fe second lines, and H and K lines. So hydrogen and potassium lines of Ca means the calcium second. At maximum light, a Cepheid may reveal mild nova-like property by exhibiting an extended atmosphere with shell ejections. These ejected shells show the spectra with strong and enhanced hydrogen and metal lines. Now we go to type II Cepheids. Near the center of our galaxy or close to the globular clusters, a group of stars, namely W Virginis stars, is identified with periods in the range from 10 to 30 days. These stars are called type II Cepheids, and their magnitude falls in the range from 0 to about minus 3.5. Their light curves are almost similar to those of type I Cepheids, except that their descending branches fall less steeply. For the same period, type II Cepheids are about 1.5 magnitudes fainter than the classical Cepheids of type I. Since both types of Cepheids follow the similar period luminosity relation, therefore we can use them as distance indicators as well. Different members in type II Cepheids are high velocity and metal poor states. They are therefore considered to be the population second stars, because we usually refer stars as population first and population second stars. So therefore they are considered to be the population second stars, having blurring in color as compared to classical Cepheids. The spectrum of these stars explain well marked bright lines of hydrogen with pronounced doubling at the maximum light. The presence of two concentric shells alternatively rising and falling above the photosphere of these stars suggests that the violent component of Ca's second doublet appears at one maximum and the red component at the next maximum. The rising and falling of the photospheric shells gives rise to the formation of the bright lines of hydrogen. The relationship of period to the apparent magnitude for the Cepheid variables in the system, like small and large Magellanic clouds, Andromeda spirals, for example M33, etc., have been investigated by several workers, namely H.S. Leavitt, H. Shapley, and E.P. Hubble. They have considered from the observational that almost all the variables are nearly at the same distance from us, indicating that there is a well-defined relationship between the absolute magnitude and the period of these Cepheid variables. According to H. Shapley, the period luminosity, that is PL curve, for any Cepheid shows how the logarithmic of the period increase as the median absolute magnitude increase. The importance of the relation lies in the fact that it helps in determining the distance scale within and beyond our galaxy. With the help of 200-inch telescope, one can detect the Cepheids at extremely large distances. If we suppose capital M and small m denote the median absolute and the apparent magnitude respectively for a star which is at a distance of r from us. For a given color axis, the following relation is valid for all the Cepheids, that is m minus m. So small m minus capital M is equivalent to 5 times logarithmic of the ratio r by 10 plus 3 times what we called as the color axis. So 3CE. The color axis in this expression is the difference between the observed and color index, and the color index of the star would have in the absence of obscuration and reddening. Beyond our galaxy, type first Cepheid are frequently observed, making them strong possible candidates for the measurement of extragalactic distances. So while using this very equation, having a relation between small m and capital M, we can talk about the color code, that is the color axis can be described. So students, let us see what we are going to learn in this module. The main aim of this lecture has been to classify variable stars in terms of groups identified by type 1 and type 2, means type 1st and type 2nd Cepheids. Type 1st variables are called classical Cepheids, and type 2nd variables are simply called as Cepheids. Subsequently, the apparent change in the brightness of these Cepheids with the passage of time lead to their analysis, rather to call better is lead to their spectrum analysis. We have remained focused with the intrinsic pulsating variables, in which changes of luminosity are mostly regular and periodic. The categorization of the variable stars have been done on the basis of the length of their periods, nature of variation of their light, and their spectral characteristics. Thank you.